Formula mass. So we talked about atomic mass and molar mass of elements. The formula mass is the average mass of an individual molecule or an individual formula unit. It's also sometimes called a molecular mass or a molecular weight. And to find the mass of an individual molecule, you just add up the masses of all the atoms that are in the molecule, right? So the whole thing is equal to the sum of its parts. Let's calculate the formula mass of calcium nitrate. So it's the mass of the formula. What's the formula? Well, we're going to have to figure it out from the name, right? So this first element, calcium, is that a metal? Yeah. So what kind of a compound is this? It's ionic. So we're going to write calcium, and what charge does a calcium ion have? 2+, because it's in group 2. And then nitrate, NO3 minus. So this nit part here tells us it's nitrogen, and then the other part's going to be oxygen. And so, like on an exam, if you're not sure, take your best guess, right? NO3 is a good guess for 8s, because a lot of the 8s are O3, not all of them, but take a guess. So then we look at the charges to figure out how to put this together, right? To balance that 2+ charge on calcium, I'm going to need 2 nitrate ions. Okay? So the formula mass then, this formula has 1 calcium and 2 nitrogens and 6 oxygens. So I've got 1 calcium, and each calcium atom weighs 40.08 atomic mass units. And I have 2 nitrogens, and each of those weighs 14.01 atomic mass units. And I have 6 oxygens, and they each weigh 16.00 atomic mass units. And again, if you are using a periodic table that has more than 4 sig figs, go ahead and use them all. I also give you permission to round to 4 sig figs, but never round to fewer than 4, because it does create problems. So I've got 40.08 plus 2 times 14.01 plus 6 times 16, 164.1 atomic mass units. That's the mass of this formula. So for significant figures, when we're calculating formula masses, you'll sometimes end up with maybe 1 or 2 extra digits, but it's never going to give you a whole calculator screen full of them, because we're just adding. And so if you just write down the whole thing that your calculator shows you, that's usually going to be just fine. Technically, this would have, depending on how you argue, it would have either 4 or 5 significant figures. Any questions? So the book gives the answer as 164.10 atomic mass units. Molar mass for compounds. So the molar mass of an element was the mass of 1 mole of that element's atoms. The molar mass for a compound is the mass of 1 mole of the molecules or formula units. And that mass would be in grams. So, example here, what's the molar mass of ammonia? What's the formula for ammonia? NH3. Why? Because it is. Yeah. There's no explanation. I told you that it was NH3, so there we are. Okay, so in one formula, we have 1 nitrogen atom and 3 hydrogen atoms. Here we're talking about a mole of these molecules. So we have a mole of nitrogen atoms and 3 moles of hydrogen atoms, right? So if we're going to write it all out really thoroughly, we could say I have 1 mole of nitrogen, and nitrogen is 14.01 grams per mole, plus 3 moles of hydrogen, and those are 1.008 grams per mole. And for units, the moles cancel out. Yeah, I got it backwards. I keep trying to remember, is it 3,4 or 4,3? It's 3,4 grams. So that is equal to 1 mole of NH3. Okay. Any questions? Calculating molar masses for compounds is an essential skill in chemistry. We do it a lot, okay? Really important. Because we use molar mass to count molecules by weighing. So just like we could count atoms by weighing, we can count molecules by weighing them. So here we're using the molar mass of the compound and Avogadro's number to help us figure out how many molecules of the compound we have. Let's find the number of ibuprofen molecules in a tablet containing 200.0 milligrams of ibuprofen. And there's the chemical formula for ibuprofen. So these come down to basically being dimensional analysis problems. So I read the problem, and there's only one number in the problem, so I'm going to write that down. 200.0 milligrams. And sometimes milligrams of what is really important. Other times it doesn't matter so much, but it never hurts to write it down. This is milligrams of ibuprofen. So that's the only number I'm given. That's my starting number. What am I trying to find? Molecules of ibuprofen. And there's no abbreviation for molecules. You have to write the whole word. Sorry. So I need to figure out, how do I get from milligrams to molecules? Moles are going to be in there, and grams are going to be in there. So moles to molecules I can do with Avogadro's number. Grams to moles I can do with the molar mass of the compound, which I can calculate. And then milligrams to grams I can do by understanding what metric prefixes mean. Any questions about the path? The path is the key to the whole problem. Once you get that written out, the rest of it should come together pretty easily. So I'm going to write out my equation using my path. So I have 200.0 milligrams, C13H18O2. And there are 3 arrows, so I'm going to have 3 fractions. The first fraction is going to grams. The second one I'm going to moles. And the third one I'm going to molecules. I'm starting with ibuprofen, I'm ending up with ibuprofen, and that suggests that I don't actually have to write that out for every single one. So I need milligrams, that unit, to go away, so I'm going to put milligrams down here. So milligrams cancel, and grams down here, grams cancels, and mole down here, and the moles cancel. Okay? Now, there aren't any conversion factors given in the problem, because between our knowledge of the metric system and the periodic table and Avogadro's number, which any decent chemist should remember, we don't need to look anything up. So grams and milligrams. Milli means what? Yeah, milli stands for times 10 to the minus 3. Those are equivalent. So if I have 1 milligram in the bottom, I have 1, and instead of writing milli, I'm going to write what it means, times 10 to the minus 3 grams on top. There are other ways to do this, but this is the only method I'm going to do in lecture. The milli, the prefix is on one side of the fraction, the 10 to the something is on the other side, every single time. Don't put 10 to the minus 3 with milli, ever, because it's wrong. Conversion between moles and grams, where do I get that? That's the molar mass that we just learned how to calculate. So I need to calculate that. I strongly urge you to show your work when you do this. You don't have to write out all the units in there, but write down the numbers, because then you can go back and double check and make sure that you got it correct. Yes?
If I write 1,000 milligrams in 1 gram, is that wrong?
That's not wrong. 1 gram is 1,000 milligrams.
That's just the way I process it.
Yeah. And some students are able to use the factors that way very successfully. My experience is that a lot of students mess those up. And so it's up to you. If you're doing it and you're getting the answers right, go for it. That's how I would do it if I wasn't teaching students. But if you're getting your metric conversions wrong, just follow the pattern. It may look a little longer, but hey, it's correct, right? And there's less thinking involved. Okay, so ibuprofen. We've got 13 carbons, 13 moles of carbon in a mole of ibuprofen, and so 13 times the molar mass of carbon, and 18 hydrogens times the molar mass of hydrogen, and 2 oxygens times the molar mass of oxygen. Punch that through in your calculator. This is what you should always do, showing your work for calculating a molar mass. So if I was going to be concerned about significant figures, it depends on, this is adding and multiplying together, and so it can get a little weird, right? How many sig figs are in my starting number? 4. My molar mass here has at least 4, possibly 5. So the number of sig figs in this isn't going to matter. Almost always in our calculations in class, the number of significant figures in your molar mass is not going to limit the sig figs in your answer. So I think it's easiest to just write them all down and ignore it. So 1 mole, 206.7. Oops, lost a digit. That's important.
I have a question in regard to that.
Yeah.
So, do you want us to just round to significant figures at the end of the problem, or do it throughout the problem?
You should always round at the end.
Okay.
Yeah. It's good to keep track of sig figs as you're going through, and with adding and multiplying mixed together, it can get a little messy. But you should never round things until the end.
Okay.
Yeah. Yeah, we'll just leave that there. So then molecules and moles. Avogadro's number, right? Does it go with molecules or moles? Molecules. 6.022 times 10 to the 23rd. 1 mole. So how do you remember that? Well, the long number goes with the long word. It's really inconvenient that way, but that's how it is, in the short number with the short word. The mole is like the chemist's dozen, and the molecules are like eggs. And so the number, Avogadro's number, is like the 12. It's 12 eggs in 1 dozen. It's never 1 egg is 12 dozen, right? Because if you put it in the wrong place, your answer's like, just like insanely wrong. Okay, so on my calculator, I'm going to take 200 times 1 EE negative 3, and I'm going to divide by 206.274, and I'm going to multiply by 6.022 EE 23, press equals, and this is what my calculator shows me, 5.83883572 E20. So that's calculator language. And if you write that on your paper, I know what you mean, but it's like baby talk, right? So we need to translate that into human math language. And we should also round to sig figs because this is our final answer. So this has 4 significant figures. This is exact. This has at least 4. And this has 4. So I should have 4 significant figures, 5, 8, 3, 8. This next one is an 8, so I round it up, 5.839. That E on my TI calculator means times 10 to the 20th molecules. Is that a reasonable answer? Yeah, it is. 200 milligrams of ibuprofen is large enough that it can be seen, right? And so if we're talking about the number of individual particles in there, it should be a ginormous number. If you're ever calculating number of molecules or atoms and you get less than 1, you've done the calculation wrong. Because you can't end up with 10 to the minus 21 molecules, right? The smallest, you can have 0 or you can have 1. Yes?
Now that you use the Avogadro's number, how would you find the atoms, the number of atoms?
Oh, that's an excellent question. And I think we get to that at some point. I don't remember which slide it's on. So the question is, okay, this is the number of molecules. How many atoms are there? Well, I would look at the formula and figure out how many atoms are in 1 molecule. So in this formula, I've got 13 atoms of carbon, 18 atoms of hydrogen, and 2 atoms of oxygen. So 13 plus 18 plus, not 20, plus 2 is what, 33? So that's 33 atoms in 1 molecule.
So would you just divide 33 into?
I wouldn't divide. So this is where units are helpful. Yeah. So instead of thinking, do I multiply by 33 or divide by 33, I'm going to write the units in first. So here I've got my 5.839 times 10 to the 20 molecules. And what I want is atoms. And I'm going to divide by molecules to make the units work out, right? Then I look at this, there are 33 atoms in 1 molecule. So I put 33 atoms per 1 molecule. And I didn't have to think, should I multiply or should I divide? I let the units do the thinking for me. Once you get the hang of it, it's really a lot easier. So if we want to figure that out, I've got the unrounded number in my calculator, so I'm just going to multiply by 33. And this is going to end up still with 4 sig figs. 1.927 times 10 to the 22 atoms. How many sig figs does this 33 have? Infinite. Yeah. I asked that because it was tricky. In one molecule, there are exactly 13 carbons, 18 hydrogens, and 2 oxygens. Because those are particles and they combine in that specific ratio and they're whole numbers. It's like, how many children are in your family? 2.3. No. There's 2 or there's 3, right? But you can't have part of a child. Any questions? .839 times 10 to the 20.